I can pick what I want the CF3 amplitude and like charge to be. And so next I'm going to describe several fundamental, I decided I wanted to do some fundamental measurements as well, which are, they're important to make. So the first one that I'll show is this reduced mobility, which is related to the drift velocity of these negative ions. Okay, how fast they're drifting in the detector to the readout. That's that. So this reduced mobility is related to that. And these show the 3 negative ion species versus the SF6 pressure. And you see that they move slower as you add more SF6, which is interesting. And then I also show it for the reduced field here. So this is the mobility for CF3 minus versus the reduced field. And you see, I do it for 2 different pressures, and you see that at a certain point, a certain reduced field, there's this kink that happens here, and that indicates that the gas has changed from thermal behavior. The negative ions are drifting in sort of this quasi like thermal with the bulk gas, but when this happens, it's in sort of a it's not drifting thermally anymore. You see that happens around like 65, 70 Townsend. And oh yeah, and then also I want to point out that this measurement, I've searched the literature, I couldn't find any mobility measurements for CF3 minus. I couldn't find any. So so the best that I could find to compare with these results is measurements of the mobility of CF3 plus, the positive ion, and that's this dashed line here. And you see it's pretty consistent with what I measured. I do the same for SF6 minus, and again 2 different pressures, mixtures that I use, and you see that there's this deviation again from flat. This deviation occurs roughly in the same place in both of them at whatever that is, like 40, 50 Townsend or so. Okay, and
this
then
is all reversible, right? If you lower the you follow back.
Yes, yeah, exactly.
In
Yes.
all these cases.
Yeah,
Right.
in all these cases, you can tune it, you can reverse it to whatever you want.
Yep.
I mean, you can't change once you've added SF6, you can't take it out. But otherwise, I mean, it's all tunable based on how you set up the experiment. So that's really cool, really exciting. We can pick what we want, and then lastly, I do the same thing for SF5 minus, and this is the measurement that I get there. And then the final fundamental measurement that I'll talk about is also a very important one, and that's diffusion, where diffusion is given by this equation here, and this is plotting the diffusion versus the electric field. And you see that this dotted line is what you would expect for thermal diffusion. If the negative ions are drifting thermally, that they should follow this dashed line. But and all these different curves here are the measurements that I made at different concentrations, and this is only a small fraction of them. I made a ton of measurements, so looking at these, you might think that if I focus on this 50 torr CF4 one, that that this might be the one to consider because it has really low diffusion, but the actual like parameter to think about isn't just the diffusion, but the diffusion over the length of the track. So and in higher pressure, this 50 torr, the tracks are actually shorter than say in this 20 torr experiment. So actually the optimal experiment or optimal mixture that I move forward with is this 20 torr CF4 3 torr SF6, which also has low diffusion but the tracks are longer. So I'm going to now show results for this 20 torr CF4 3 torr SF6 mixture. And again, these signals are using the laser. So when I fiducialize them, they are centralized on 58.3 centimeters, the entire length of the detector. And so the red is fiducialization with the SF5 minus peak, the typical one, and then the blue is with the new species. And although this shows that the resolution is slightly worse for CF3 minus, that doesn't show everything. I show here that the fiducialization efficiency with the CF3 minus is like 2 times better than it is with SF5 minus. And so here I do an experiment with the neutron generator. Again, cathode means on the cathode side, gem means on the gem side of the experiment. And this is fiducialization, not skewness, fiducialization. So this is where the event occurred inside the detector. And you see that the red has many more events than the blue. And then it also you see based on the shape of these curves, that's also interesting. That shows that that there's more nuclear recoil events closer to the DD generator. So when the DD generator is on the cathode side, you see that there's more events at high Z, and then when it's on the gem side, there's more events at low Z, close to the readout. So that's pretty cool too. But yeah, so that's good. And want to just reiterate that this solves that fiducialization issue in SF6, and it also increases the fiducial volume of our detector, where you notice the CF3 minus peak is much faster than the SF5 minus peak, which means that this time difference, I can resolve a track smaller in Z, is what that means. And so this is really cool. And then last thing I'll talk about is I take this optimal mixture that I chose, this 20 torrs, this mixture, and I measure the the discrimination and the directionality, similarly to what I showed earlier. So the analysis, everything else will be the same, so I won't show that all again. But I will point out that I learned a little bit from those measurements. And what I did is I measured the discrimination and the directionality in 2 separate experiments. So I first measured the discrimination by adding lead bricks to attenuate the gammas, and then and since I do that, I can lower the energy threshold to 6 kVEE, which is low, and then that means that I can measure directionality or discrimination down, or at least up to that, or potentially up to that. And then I can do a cobalt-60 experiment and a background experiment to define the nuclear recoil band and separate in that separation. And then I then do it, but unfortunately doing this, the nuclear recoil rate is still low. It's still low. So I can't do this to measure directionality because I need a lot of nuclear recoil statistics in a given energy bin in order to measure directionality. So that solution doesn't work for this. And what I do here is no lead bricks, and I do a 20 kVE trigger threshold to there. Okay, so here right into some results. So here's the cobalt-60 experiment again, or I do another one, and the red is the electronic recoils. The black are the background RPR events, which again they reside in the nuclear recoil band. And with this, I define the blue dashed line here, the separation between the 2 of them, and and so I define this nuclear recoil band. And then if I plot this in terms of the range versus energy, I get this result here. You can see the vertical electron band and then the nuclear recoil band there. And then the same thing, I also did a background experiment where I just let my detector sit there and I let ambient background radiation interact in my experiment. And you see the results. The results are the same. And this blue dashed line is sort of the where I utilize both of these 2 data sets to define it. And so that's what I do there. And then this is my discrimination measurement that I get with this low threshold. And so that's the full thing. But if I zoom in at low energy, you see that I have the electronic recoil band here, what I've defined to be the nuclear recoil band, and you see we have discrimination down to like 15 kVE, which is much better than what I had before. I had like 50 kV before, so this is pretty cool, pretty good. And and again, this is with a 1D readout, 1D the Z dimension. Okay, so that's the discrimination, and then the directionality. So this is the range versus energy for the directionality. Again, So I've raised the trigger threshold to 20 kVe, and you see there's a lot of on this figure. And the reason is because of several things. So the first one is that there's this, so the black and below is the nuclear recoil band, what I've defined to be the nuclear recoil band, and above it are these haze events. I call them the haze, because we have an idea for what they are. So we think what they are is they don't show up in any other experiments. They don't show up in the background or the cobalt experiment. So we know that they're related to the DD generator, the neutron source. And so what we think they are is they're neutrons interacting in the acrylic of our detector and liberating a proton that recoils through the entire width of the detector. So then those events would be really long at a given energy. So that means they would reside up in this region, and so that's this haze. And then below here, I also remove this bottom region. I only do the directionality measurement on the black, and I remove these short nuclear recoils from the analysis because if you measure their directionality, their skewness, it's consistent with zero. It doesn't provide anything to the measurement. So I focus on this band here, and this is the result that I get, the directionality. Again, the skewness difference versus energy, and you see it's pretty good. You see that as I increase the energy, there's more skewness, more directionality that I measure, and you see that in this lowest energy band, I have pretty significant measurement, and I get that I have directionality in this lowest band down to 30 kVe. And I want to point out the black curve. So the red is including the entire black band, but the black curve on here is where I've looked at the longest 2/3 of the track. So I've further removed some events, looked at the longest events, and they have even better directionality. So that's also really cool. And yeah, so those are my measurements, and here's some ideas that I had that we had on how to improve those measurements. And I actually have aspirations to do this. But the first one is to use a readout board like the one I designed here with a veto wire to reject that haze. So the protons would go across the entire thing, and we'd see it on the veto wire, and we could remove them. So that the haze we could completely get rid of. And then the other thing is to use a fast data acquisition system. Remember the oscilloscope 1 second dead time. So if I could have like this here, if I could have a faster data acquisition system, I could acquire nuclear recoil statistics faster, and I could more efficiently do that. And yeah, so that's how I would improve my measurements further. And here's the summary. So the first thing I talked about was discrimination and directionality in a low pressure SF6 TPC using a windy readout, reading the signal out in the drift dimension. And then I talked about how in SF6 there was low fiducialization efficiency due to this small SF5- peak, and we did work toward enhancing that. And in doing that, I unexpectedly discovered this new negative ion species that I believe to be CF3-, and I found that this peak is tunable in terms of the drift field and the SF6 concentration that you add to the mixture. And so I chose this 20 torr CF4 3 torr SF6 mixture, and I focused on it, and I measured the fiducialization, and I showed that it's much more efficient than SF5- fiducialization. And then I further took that and I measured the discrimination and directionality in that mixture, again using windy readout. And I got some pretty good results there. And I would improve them, as I just said, with a readout board with a veto wire to remove the haze and a faster data acquisition system. Okay, so I'd like to thank Dinesh Lumba for helping me along, giving me direction, giving me lots of advice and sometimes criticism, but but helping me do it. I'd like to thank Eric Lee. So Eric Lee, he's not here with us, but he designed several of these experiments. Actually, that cylindrical detector that I showed, he designed it, and also several other gadgets and gizmos that I've used throughout my time here. He designed them. So he's a really good engineer, and we'll miss him. But then I'd also like to thank Wen, who was a grad student before me, and he helped me get along, and he helped me do some of the SF6 stuff, and got me moving toward that, and gave me like a head start. and then I'd like to thank Alex Mills for being really like creative, having creative ideas, and being honest to like tell me when he thinks my ideas are dumb and whatnot. So he'll be taking over a lot of the stuff that or some of the stuff that I showed here, and yeah. Okay. So if people have questions, I'm gonna get a drink of water.